March 1944. At Rechlin Lärz Airfield in Mecklenburg, Germany, the workday began, as it often did, for the technicians and engineers of the Luftwaffe's Technical Intelligence Service, with another captured enemy aircraft waiting to be dissected. At Airprobung Stella Rechlin, the Reich's primary test and evaluation center, this had become a systematic routine. Every new Allied machine that could be dragged in, intact or in pieces, was studied, catalogued, flown if possible, and stripped of its secrets. By this stage of the war, these examinations were not an academic exercise. They were a matter of survival. The air war over the Reich was intensifying, and the Luftwaffe's leadership depended on Rechlin's technical reports to understand why the enemy seemed to be reaching ever deeper into German airspace with growing confidence. The engineers at the facility were used to surprises, but what arrived by rail on March 6, 1944, would alter their understanding of American capability in a way few of them forgot. On that day, a captured P-51 Mustang, still a relatively new presence over Germany, was unloaded from a railway flat car. The fighter had been shot down 2 days earlier near Brandenburg during what German intelligence believed to be the first American single-engine fighter-escort mission to Berlin. The pilot had been killed on impact, but the aircraft, battered and scarred, was largely intact. For the technical staff, this was a rare prize, a nearly complete example of the fighter that, in combat reports, was described as changing the balance of air power over the Reich. Hermann von Bombach, an officer involved in aircraft development who would later command Kampfgeschwadron, oversaw the initial inspection. As technicians worked their way through the cockpit, they came across the young American pilot's navigation charts, still folded and marked in pencil. The plotted course traced a line from an airfield at Debden in England across the North Sea to Berlin and back again, a round trip of more than 1,000 miles. It was a simple artifact, just paper and ink, yet it posed a question that went to the heart of German defensive planning. The technical evaluation began immediately, because German intelligence had been wrestling with troubling reports for weeks. Luftwaffe pilots and radar stations had observed American fighters appearing deeper and deeper inside the Reich. Yet official assessments still insisted that single-engine fighters lacked the fuel capacity to escort bombers all the way to Berlin. The geometry seemed clear enough. The distance from English bases to the German capital was approximately 560 miles in one direction. For a round trip, a fighter would need the fuel for that distance, plus reserves for climb, combat, and diversion. Earlier captures appeared to confirm the German view. Detailed analysis of P-47 Thunderbolts and P-38 Lightnings had shown that, even with external fuel tanks, these fighters could not penetrate far beyond Western Germany before their range limits forced them to turn back. The Luftwaffe's defensive strategy had evolved accordingly. Allow the escorts to come as far as their fuel permitted, then fall on the bombers once the fighters were forced to leave. That logic began to crack on March 4, 1944. On that day, P-51 Mustangs of the 4th Fighter Group, which had transitioned from P-47s only days earlier, escorted a small bomber force toward Berlin. The mission itself was hampered by weather and communications problems. Only 32 bombers reached the target. But the essential fact could not be dismissed. American single-engine fighters had flown with the bombers to the capital of the Reich, fought there, and then returned to England. 2 days later, on March 6th, the scale increased dramatically. Approximately 660 bombers went in daylight against Berlin, and this time they were escorted not by a token force, but by a heavy screen of fighters. More than 150 P-51 Mustangs, supported by P-38 Lightning and P-47 Thunderbolt groups. The escorts met the Luftwaffe interceptors over the city and then accompanied their charges on the long journey home. 2 missions, 48 hours apart, showed that this was not a freak success or a single daring penetration. The Americans had clearly solved the escort fighter problem that German planners had long considered unsolvable. General Major Adolf Galland, General de Jagdflieger of fighters, and one of Germany's most successful aces with over 100 victories, did not rely only on reports. Despite his administrative rank, he continued to fly combat. In engagements over Germany, he encountered the P-51's first-hand. In his assessments, submitted through official channels, he noted with unease that American fighters were not behaving like aircraft at the ragged edge of their fuel endurance. Over Berlin, they operated at full combat power, maneuvering aggressively, diving, climbing, and pressing attacks without visible concern for conservation. They were not nursing their tanks. They appeared to have reserves. This contradicted everything the Luftwaffe believed about American fighter range. The P-51 might be fast and agile, but how could a single-engine fighter sustain combat over Berlin and still make it back across the North Sea? At Rechlin, the technical team set out to answer that question the only way they knew, by measuring, calculating, and testing. They began with the basics, the P-51B's internal fuel capacity. Under each wing they found a main tank holding 92 gall of aviation gasoline, a total of 184 gall in the wings. Behind the cockpit they identified a fuselage tank, an 85 gall reservoir positioned directly aft of the pilot. This internal fuselage tank, the team learned, had been a relatively recent production change, added to extend range. Together, the three tanks gave the aircraft 269 gall of internal fuel. The Packard-built Merlin engine under the cowling, a licensed version of the Rolls-Royce Merlin that had transformed the Mustang's high-altitude performance, had known consumption rates. At economy cruise settings, it burned roughly 60 gall per hour. At normal cruise power, the figure rose to around 75 gall per hour. For their calculations, the engineers took an approximate cruise consumption of 70 gall per hour and began to work through the numbers. On paper, with 269 gale and consumption at that rate, the P-51B could remain airborne for around 3.8 hours. At a cruising speed of about 300 mph, this gave a theoretical maximum range of roughly 1,140 mph. That was just sufficient, in theory, to reach Berlin from English bases and return, with little margin. It certainly did not seem to leave comfortable reserves for extended combat over the target area. Yet combat reports told a different story. German pilots described dogfights above Berlin lasting 15 to 20 minutes before American fighters disengaged and headed west. They spoke of Mustangs that did not shy away from high-power maneuvers. At combat settings, the Merlin's fuel consumption climbed to more than 100 gall per hour. Logically, such expenditure should have left many escorts short of fuel long before they reached home bases. The arithmetic did not match the reality being observed in the skies. Somewhere, a factor was missing. The first hint of that missing element appeared when engineers at Rechlin examined the Mustang's wing structure more closely. Under each wing, they found standardized hard points designed to carry external stores. The fittings were not just simple attachment lugs. They included fuel line connections. That meant they were designed specifically to feed external fuel tanks, drop tanks, into the aircraft system. Drop tanks were not novel. The Luftwaffe had used them since the Battle of Britain. Bf 109 fighters often carried 300L tanks. FW-190s used external tanks for long-range missions. All major air forces employed the same principle: carry additional fuel externally, then jettison the empty tanks before entering combat to regain performance. The Germans knew this practice well, so the question at Rechlin was not whether the Americans used drop tanks, but what kind and in what quantity. Given the range that the Mustangs were demonstrating, the answer had to lie outside the airframe that now sat in the hangar, stripped and silent. The hunt for that answer began in the fields and forests northeast of Berlin. Within hours of recognizing that the P-51's wing racks were designed for fuel tanks, Luftwaffe intelligence officers plotted where those tanks were most likely falling. Based on reported engagement points from Luftwaffe pilots and estimates of when fighters would have jettisoned their external stores, they drew arcs across maps of northeastern Germany. Wherever Allied fighters met German interceptors, there was a high probability that empty tanks had rained down. Search teams were assembled from Wehrmacht units, and Hitler Youth volunteers. They fanned out across farmland and woodland, moving through winter-bare fields, snow-dusted forests, and marshy ground. Their orders were simple. Any unfamiliar metal or cylindrical object found in the wake of air battles was to be reported and recovered, if possible. Most of what they found in those first days was wreckage, twisted fragments, crushed shells, torn fittings. Many tanks, dropped from altitude at speed, had hit the ground hard and disintegrated. Some smashed into forests and shattered against frozen earth. But persistence paid off. Within 3 days, several drop tanks were delivered to Rechlin. Most were damaged, but 2 had come down in soft soil or winter wheat and survived with their basic structure intact. At first glance, these were unremarkable objects, cylindrical, tapering to nose and tail, about 108 in length and roughly 22 in diameter at their widest point. Capacity calculations based on dimensions and internal volume gave a figure of around 108 US Gaull, approximately 400 L per tank. 2 such tanks, one under each wing, would add 216 Gaull to the aircraft's 269 Gaull of internal fuel, bringing total capacity to 485 Gaull. With that amount of fuel, the P-51's endurance at cruise power climbed to around 6.7 hours, and its theoretical range exceeded 2,000 miles. Suddenly, the numbers made sense. A fighter with that fuel load could escort bombers to Berlin, linger in the target area, fight, and still return with meaningful reserves. The mysterious extra fuel that combat behavior implied was accounted for. Yet when the engineers at Rechlin turned their attention from capacity to construction, they found something even more striking. Running a hand along one of the tanks, a materials specialist paused. The surface did not feel like metal. The silver paint covering the exterior rang dull when tapped. There was no familiar cold hardness of aluminum or steel beneath. Careful scraping near the tail cone exposed the truth. Beneath the thin metallic-colored coating were multiple layers of heavy paper, each roughly 0.5 millimeter thick, laminated together with some kind of rainous adhesive. The tank, it turned out, was not metal at all. It was made of paper. They examined the structure in more detail. The nose and tail sections had been formed from overlapping pieces of the paper material, pressed into shape in a process reminiscent of papier-mâché. The overlapping sections left subtle ridges where one piece overlapped another, giving the surface a faintly scalloped texture. The central cylindrical body, by contrast, was seamless, continuous layers of paper wrapped around a form until the required thickness and strength were reached. Fuel fittings told a different story. The inlets and outlets were brass, neatly machined, properly threaded, and sealed. Through the open filler neck, the investigators could see the inside of the tank coated with a glossy layer that appeared to be a cellulose-based lacquer, intended to protect the paper and adhesive from the corrosive effects of aviation gasoline. German materials experts were called in to analyze the construction. They identified the base material as kraft paper produced through chemical pulping that yielded particularly strong cellulose fibers, the same family of material used for heavy-duty shipping containers and industrial packaging. The adhesive was determined to be a resource-null formaldehyde resin, a thermosetting polymer that, once heat-cured, created bonds stronger than the paper itself. Counting and slicing samples revealed at least 12 separate layers of paper, each oriented to distribute loads and provide strength in multiple directions. Inside the tanks, wooden anti-slush baffles had been installed to prevent fuel from surging violently during maneuvers. Nothing about the design was improvised. It was clearly standardized, engineered for repeatable mass production. When they weighed the empty tank, the result was another surprise. At about 80 lb, it was not dramatically lighter than a comparable metal tank of smaller capacity, which typically weighed between 65 and 75 lb. The advantage was not in weight. It lay elsewhere, in materials and manufacturing. For the personnel at Rechlin, the implications came quickly into focus. The Americans were building fuel tanks from non-strategic materials. paper and wood-based resins did not require the aluminum, steel, or other critical metals that every wartime economy struggled to secure. No sheet metal forming machines were needed for these tanks, no skilled welders, no highly trained metal workers. In principle, any paper mill or packaging plant equipped with presses and curing ovens could be adapted to manufacture them. The United States, they knew, had hundreds of such facilities. Intelligence officers began rough estimates. Before the war, American paper production stood at roughly 12 million tons per year, and war mobilization had only increased that figure. If even 1% of that capacity were devoted to drop tank production, the resulting output would exceed 100,000 paper tanks per month, far more than any single fighter type could consume. In practice, the limiting factor would not be raw material, but equipment and labor. Yet the work itself, cutting, laminating, bonding, and assembly, could be done by semi-skilled personnel after short training. The tanks themselves seemed to underline this point. They carried no visible serial numbers or manufacturer markings. Nothing suggested a limited or precious item. They were, in effect, a commodity. Cheap, standardized, and completely expendable. As more information arrived, the picture grew sharper. The paper tanks, it turned out, were strictly single-use devices. The resorsol adhesive that held them together, while strong when cured, would slowly break down if exposed to gasoline for extended periods. Intelligence reports and interrogations of captured American aircrew indicated that these tanks had to be filled shortly before flight and could not remain full for more than a few hours without risking leaks. In operational terms, this did not matter. Fighters were fueled as part of pre-flight preparations. The tanks did their job for a few hours and were then jettisoned. In practice, the single-use nature of the tanks simplified logistics. There was no expectation of recovery, cleaning, inspection, or repair. Once empty, they were meant to be discarded. Supply officers ordered new ones. Paper mills made more. The engineers also noted the practical details of field identification. Paper drop tanks used by American forces were painted silver, while metal tanks were painted gray. The color coding allowed ground crews to distinguish types at a glance, helping them match tanks to mission profiles. The silver paint on paper tanks had an additional advantage. It reflected sunlight, reducing heating of the gasoline within, and thus helping to control evaporation and vapor pressure issues at high altitude. By late March 1944, German intelligence traced the origin of these paper tanks not to American designers, but to British initiative. In 1943, facing acute shortages of strategic metals, the British Air Ministry had commissioned development of impregnated paper fuel tanks to conserve aluminum. The Bowater-Scott Corporation, drawing on its expertise in large-scale paper manufacturing, developed the production process. The tanks entered service with RAF fighter squadrons in late 1943. The Americans, recognizing the utility of the concept and unburdened by severe aluminum shortages, adopted the design quickly. Multiple manufacturers in Britain and the United States began producing tanks for USAAF fighter units. An innovation born from British scarcity was being exploited on a far larger scale by American industrial capacity. By the time the engineers at Rechlin completed their initial analysis, they understood that they were not just looking at a clever fuel container. They were holding a distilled symbol of Allied industrial methods, an object that encapsulated the way the enemy thought about production, materials, and war. The paper drop tanks forced the technical staff at Rechlin to widen their focus. If the Americans were willing to build something as vital as a fuel container out of laminated paper, what did that say about their broader approach to war production? The tank was not sophisticated in the way German engineers usually admired. It was the opposite, a deliberately simplified solution, optimized not for maximum performance, but for ease of manufacture, low cost, and minimal use of critical resources. Prompted by this realization, German analysts began a systematic review of captured American equipment with fresh eyes. They found a recurring pattern. American weapons and vehicles were not always superior in terms of individual component performance. German optics often outclassed American sights. German small arms sometimes showed more refined mechanical design. German armor metallurgy, in certain respects, was more advanced. But when they examined production, standardization, and field reliability, the advantage shifted decisively. American equipment was consistently better in those dimensions. Components were designed from the outset for mass production by semi-skilled workers. Parts were interchangeable without hand-fitting. Tools and jigs were standardized, assembly lines were optimized, and tolerance ranges were chosen with manufacturability in mind. The results were machines that might not impress a craftsman for their subtle engineering, but could be produced, maintained, and replaced at an astonishing rate. Against this stood the German model. Many German weapons and vehicles were technical masterpieces. A German tank engine or aircraft power plant represented the peak of precision engineering. Production, however, depended heavily on skilled labor, specialized tools, and time-consuming processes. Bottlenecks appeared wherever master craftsmen or high-precision equipment were required. The more complex and refined the design, the more difficult it became to manufacture in quantity. The contrast was stark. The Germans built superior individual items. The Americans built good enough items in overwhelming numbers. In an industrial war, that difference could be decisive. The P-51 Mustang itself provided a case study in this philosophy. North American aviation had designed the original Mustang prototype, the NA-73X, in response to a British requirement in 1940. The time from contract to completed prototype was just 117 days, one of the fastest concept-to-flight cycles in aviation history. The first flight took place on October 26, 1940. That pace would have been nearly unthinkable under German development practices. By 1944, North American was building P-51 variants at two main plants. At Englewood in California, peak production averaged around 364 Mustangs per month. The Dallas plant added further output. Combined, these facilities turned out an average of roughly 574 P-51s per month during 1944, with production accelerating as the year went on. In January 1945, monthly Mustang output would reach a peak of 881 aircraft. Each P-51 contained about 15,000 individual parts, many supplied by subcontractors scattered across the United States. The Packard-built Merlin engines that powered the aircraft rolled off production lines in Detroit at rates above 300 units per month. Final assembly of a P-51D required about 22,000 man-hours of labor, but those hours were distributed along an efficient production line. At peak efficiency, completed Mustangs left the factory doors at intervals of just a few hours, roughly one new aircraft every 2 hours. When German analysts compared these figures with their own, the imbalance was sobering. Messmid and Fowler-Wolf, the main producers of Bf-109 and FW-190 fighters, together achieved output of approximately 600 fighters per month in early 1944, under emergency measures and with increasing reliance on forced labor. Despite all efforts, German aircraft production could not approach American and Allied volumes, and it was carried out under the persistent threat of bombing. The resource picture was no more encouraging. American aluminum production in 1944 reached about 1.25 million tons per year, roughly 2.5 billion pounds. This represented a spectacular expansion from pre-war output of around 164,000 tons in 1939. Germany's own aluminum production, by comparison, peaked at roughly 250,000 tons annually and was already declining as bombing raids struck smelters and the Reich lost access to key bauxite sources. The Americans, in other words, had around 10 times Germany's aluminum production capacity. From this perspective, the decision to build drop tanks from paper rather than metal took on a different meaning. It was not an act of desperation. The United States could have made every tank from aluminum if it had wished. Instead, planners chose paper because it was cheaper, required less specialized equipment, freed aluminum for other uses, and could be turned into finished products quickly by a broad industrial base. It was optimization, not shortage. The psychological impact of this realization spread through the Luftwaffe's technical and operational circles. The paper drop tank became a talking point in briefings, a prop used to explain the nature of the war Germany was fighting. At technical conferences, captured tanks were passed around, their layered construction pointed out, their capacity numbers explained. Pilots preparing to join frontline units were shown the tanks and asked to calculate what they meant for escort range. The conclusion was unavoidable. With such tanks, American fighters could escort bombers to any point in Germany. The consequences were already visible in loss statistics. Galland, in his operational assessments, emphasized that the P-51 was superior to German fighters above 20,000 feet. Against the Bf-109 at altitude, it was faster. Against the FW-190, it was more maneuverable. With extended range from drop tanks, it could stay with bomber streams throughout their missions. There would be no more predictable points where escorts turned back, leaving bombers briefly exposed. As 1944 progressed, loss figures confirmed the shift. In January, the Luftwaffe lost around 90 fighters, while claiming approximately 150 Allied aircraft destroyed. By February, German losses had climbed to about 160 aircraft, while Allied losses rose to roughly 230. The trend line pointed only one way. The Allies could replace their losses more rapidly than Germany could inflict them. For the officers and engineers at Rechlin, the paper drop tank, the Mustang production numbers, and the aluminum statistics all told variations of the same story. Germany was fighting an enemy whose industrial base dwarfed its own, and whose methods were tailored to exploit that advantage to the full. The implications for the coming summer's air battles were grim. The summer of 1944 brought those implications into brutal clarity. With long-range escorts now routinely available, the 8th Air Force launched deep penetration raids almost daily whenever weather allowed. P-51 Mustangs, P-47 Thunderbolts, and P-themed Lightnings flew alongside bomber formations from England to targets across Germany and back again. The Luftwaffe, which had once been able to disrupt unescorted bomber streams at great cost to the enemy, now faced those same formations heavily guarded from assembly point to target and homeward leg. Luftwaffe fighter units were ordered to adapt. Fighter controllers attempted to concentrate their forces at specific points along the bomber routes to achieve local numerical superiority. This demanded precise timing, long-range coordination, and careful fuel management. Dispersed units had to converge over planned intercept zones at the right moment, at the right altitude, and in sufficient strength to break through the escort screen. In theory, the tactics might have achieved isolated successes. In practice, fuel shortages, communication problems, and the ever-present escorts undermined them. Units struggled to assemble in time. When German formations did manage to mass effectively and reach the bomber streams, they found P-51s waiting. Battles that once had been fought between German fighters and largely unprotected bombers were now first battles for air superiority, fought against escorts that were often more numerous and flown by increasingly experienced pilots. Losses mounted quickly. In June 1944, approximately 350 day fighters were lost in defense of the Reich. In July, losses in the West alone exceeded 350 single-engine fighters, representing a monthly attrition rate of 31.2%. August numbers were similar, with an attrition rate reaching 36%. At such rates, the Luftwaffe's pool of seasoned pilots shrank rapidly, replaced by newcomers whose training could not match that of their predecessors. By this period, American pilots often arrived in theater with 300 hours or more of flying time behind them. German replacement pilots, by contrast, might have accumulated around 150 hours in total, and sometimes far less in their assigned aircraft type. Many received as little as 30 hours in type before being sent into combat. Under these conditions, every sortie became more dangerous. Numerical inferiority, the constant presence of escort fighters, and the experience gap between opposing pilots combined to make daylight operations over Germany increasingly lethal for Luftwaffe units. At the same time, the question arose within technical and planning circles: could Germany adopt a similar paper drop tank system? From a purely technical standpoint, the answer was yes. German chemical companies could manufacture suitable resins. German paper mills could produce strong kraft paper. The lamination, curing, and assembly processes were within national industrial capabilities. Yet when the idea was examined in terms of practical feasibility, the answer turned negative. The chemical industry was already stretched to its limits, producing synthetic rubber, explosives, and other essential war materials. Diverting resin to non-critical uses was not acceptable. The paper industry was fully engaged meeting military demands for maps, documentation, and packaging. Beyond that, the primary bottleneck was no longer range. By late 1944, fuel shortages were grounding large portions of the Luftwaffe. Training hours were slashed. Operational sorties were dictated more by fuel availability than by tactical need. Building paper drop tanks to extend range held little meaning when there was barely enough fuel to conduct short-range local defense. For planners at higher levels, the irony was bitter. The Americans had solved the fighter-escort range problem with a disposable paper fuel tank at the very time when German fighters were increasingly tied to their airfields by lack of fuel. Two sides faced very different constraints and arrived at equally different outcomes. The Americans had more of everything: aircraft, fuel, pilots, aluminum, and industrial capacity. They had enough excess capability to optimize designs and processes, to choose materials for efficiency rather than necessity. Germany, by contrast, was fighting a war of scarcity on every front. By January 1945, the broader strategic picture was unmistakable. Soviet forces were approaching the Oder River, bringing them to within less than 50 miles of Berlin. In the west, Allied armies had recovered from the Ardennes offensive and were pushing towards the Rhine. The Luftwaffe, once dominant in European skies, could now mount only sporadic resistance, and even that was constrained by fuel and the shrinking cadre of experienced pilots. At Rechlin, the systematic study of American equipment continued, but it increasingly resembled an archival effort rather than a race to find exploitable weaknesses. Engineers compiled data, documented designs, and refined their assessments, knowing that their findings could no longer alter the course of the war. The final comprehensive analysis of the P-51 and its drop tanks was prepared in late January 1945. It catalogued every technical facet of the Mustang's range: internal fuel system, drop tank capacities, construction methods, projected production volumes, and operational consequences. The report's conclusion was direct. The P-51 Mustang, equipped with expendable paper drop tanks made from non-strategic materials, had rendered the German heartland indefensible against American daylight bombing. Germany lacked the industrial base to rival American fighter production, lacked the fuel to sustain air operations on the necessary scale, and lacked the trained pilots to offset current attrition rates. The findings were filed in the Reich Air Ministry archives. Whether they were read by senior leadership is unknown. By then, the facts they contained were daily visible in the skies over the Reich. Even as the war approached its end, the Luftwaffe used captured Allied aircraft in specialized roles. At Rechlin's June 1944 exhibition, multiple Allied aircraft were displayed for Luftwaffe personnel: P-51 Mustangs, B-17 and B-24 bombers, P-38 Lightnings, Lancaster and Mosquito bomber types, Typhoon fighter bombers, and various Spitfire variants. Thousands of pilots and ground crew walked past these machines, studying their shapes, inspecting their engineering. Paper drop tanks were positioned prominently, accompanied by diagrams explaining their construction and the dramatic effect they had on escort fighter range. The exhibition served both as technical education and as a visible reminder of the scale and quality of Allied production. Kfk 200, the Luftwaffe unit responsible for special operations, including flying captured Allied aircraft, also operated several P-51s during 1944. Test and evaluation flights revealed what combat pilots already suspected. Reports from KG-200 pilots praised the Mustang's cockpit visibility, especially in the later P-51D with its bubble canopy, its stable handling, responsive controls, and excellent high-altitude performance. The Merlin engine was noted for its smooth power delivery, reliability, and consistent performance across the flight envelope. Most striking of all for the German test pilots was the aircraft's range and endurance. With full internal fuel and drop tanks, they recorded that the Mustang could stay aloft for more than 6 hours, flying mission profiles no German single-engine fighter could match, even when fitted with external tanks. These flights, along with the technical work at Rechlin, informed what remained of Luftwaffe tactical doctrine in the war's final year. Fighter controllers understood that American escorts would accompany bombers for the entirety of their missions. As a result, every attempt to reach the bombers first required breaking through a strong fighter screen. In 1943, unescorted or lightly protected bomber formations had borne catastrophic losses. By mid-1944, that dynamic had reversed. German fighters attempting to reach the bombers now suffered the catastrophic losses. While engineers and officers struggled with operational realities, the civilian population experienced the war's industrial imbalance in another way. Paper drop tanks continued to fall across Germany in 1944 and into 1945. Civilians grew accustomed to finding the distinctive cylinders in fields, ditches, and forests. Early reports often mistook them for unexploded bombs, leading to local alarm until authorities clarified their purpose. Civil defense organizations distributed instructions explaining that the silver cylinders dropped by Allied aircraft were empty fuel tanks, not weapons. Even so, their psychological effect was recorded in morale reports. The sight of enemy aircraft overhead in such numbers that contrails crisscrossed the sky, while the same aircraft casually discarded large, expendable fuel tanks made of paper, drove home the disparity in resources. To a society rationing every liter of gasoline and every kilogram of metal, the notion of throwing away fuel containers after a few hours' use was a potent symbol of the opponent's strength. The war ended in May 1945, but the story of the P-51 Mustang and its paper drop tanks did not end with the capitulation of Germany. As occupation forces and museum curators surveyed the debris of the conflict, very few intact paper tanks were found. Most had been crushed on impact or deliberately destroyed by Allied ground crews to prevent any reuse. The objects had been designed as expendables, and most had served precisely that function. A handful of surviving examples, however, were collected and preserved. In time, some of these tanks reached museums. The National Air and Space Museum in Washington, for example, maintains several paper drop tanks in its collection, displayed alongside the P-51 Mustangs they once fed. Information placards describe their construction from laminated kraft paper impregnated with phenolic resin, their 108 Gaull capacity, and their manufacture by companies such as Bowater Scott. The signage rarely mentions the weeks German engineers spent poring over these paper cylinders at places like Rechlin, nor the psychological shock they caused. That part of the story lives on primarily in technical reports and post-war memoirs. Those accounts reveal how deeply the tanks impressed German technical personnel. They were not examining a revolutionary weapon. The paper tank was not an advanced piece of engineering in the sense German designers usually respected. It was simple by design, intentionally stripped of unnecessary refinement. Yet this simplicity conveyed a message more devastating than any high-precision device could have delivered. It demonstrated that the Allies, and particularly the United States, had such overwhelming industrial capacity that they could afford to optimize for mass production, efficiency, and resource allocation, rather than for technical perfection. The Germans who handled those tanks recognized at once that they were not facing an enemy improvising under pressure with substitute materials. They were facing an enemy wealthy enough in resources that substitution was a strategic choice made for efficiency, not a constraint imposed by lack. For experienced engineers schooled in the realities of their own country's shortages, that realization was hard to ignore. Post-war interrogations of Luftwaffe personnel returned repeatedly to this theme. When asked when they first understood that Germany would lose the war, many technical staff and senior officers pointed to the early spring of 1944. The appearance of long-range fighter escorts over Berlin was, in their view, the decisive indicator that the strategic balance had shifted irreversibly. Hermann Göring, interrogated after the war, acknowledged that long-range fighters had inflicted a major strategic blow on German defensive planning and were among the most decisive factors in the outcome of the air war. While a specific quote attributed to him about Mustangs over Berlin remains unverified in primary sources, his post-war statements consistently emphasized that Allied air superiority, made possible in large part by long-range escort fighters, had been central to Germany's defeat. The technical lessons extracted from the P-51 and its paper drop tanks did not disappear after 1945. Many German engineers who had worked at facilities like Rechlin later immigrated to the United States or cooperated with Allied technical intelligence agencies. Their detailed understanding of American production methods and design philosophy influenced post-war aviation and industrial development. Concepts that had been observed, standardization, interchangeability, and design for manufacturability, became accepted norms in aircraft design and broader engineering practice. The paper drop tank itself became a case study in wartime innovation. In engineering schools and military staff colleges, it was used as an example of how resource optimization and industrial scalability could yield a strategic edge. The tank demonstrated that an effective solution did not need to be elegant or technically impressive. It needed to be appropriate to the problem, extending fighter range in a way that was fast, cheap, and compatible with existing industrial capacity. That principle extended into modern systems engineering. The best solution is not always the most sophisticated. The best solution is the one that meets operational requirements, can be manufactured in the needed quantities within the available time, and uses resources that can be supplied consistently. The paper tank, glued together from layers of kraft paper and resin and discarded after a single mission, embodied this idea as clearly as any wartime device. The Mustang that carried those tanks into combat also left a long legacy. As one of the most successful fighter designs in aviation history, the P-51 combined range, performance, reliability, and producability in a way that made it an ideal escort fighter for the strategic bombing campaign. Its effectiveness was not the result of a single breakthrough. It arose from the interaction of multiple elements: an aerodynamically efficient airframe shaped by North American Aviation's engineering team under Edgar Schmood, the powerful and dependable Merlin engine, the added fuselage fuel tank that extended internal range, and the availability of drop tanks, including paper tanks, that pushed the fighter's operational radius beyond 800 millitons. Produced in large numbers, more than 15,000 Mustangs built during and immediately after the war, the aircraft remained in service for decades. In Korea, it flew primarily in ground attack and close air support roles, where its endurance proved as valuable as it had in European escort missions. Some air forces kept P-51s in frontline use into the early 1980s, a testament to the underlying soundness of the design. Today, over 100 Mustangs remain airworthy, maintained by collectors and museums around the world. When one of these aircraft takes to the air, often still painted in wartime colors, it recalls not just the dogfights over Europe, but the industrial system that made such aircraft available in thousands. The broader historical meaning of the P-51 and its paper tanks reaches beyond individual battles. They illustrate a central reality of industrial warfare. Conflicts between modern industrial nations are decided as much in factories and shipyards as on battlefields. During World War II, the side that could produce more aircraft, more vehicles, more ammunition, and more supplies, and could do so faster than those assets were consumed, held a decisive advantage. American industrial mobilization in 1943-1944 reached unprecedented levels. Aircraft production exceeded 50,000 per year. Shipyards launched vessels at a pace of multiple ships per day. Ammunition output reached billions of rounds. These resources supported not only American forces, but also equipped Britain, the Soviet Union, and other allies through Lend-Lease. Germany, despite its technical expertise and significant industrial capacity, could not match that scale. Strategic bombing, loss of raw material sources, competing priorities, organizational inefficiencies, and the sheer disparity in base capacity all combined against it. Fundamentally, Germany fought a coalition whose combined industrial might was several times greater than its own. Once American production reached full mobilization, Axis defeat became a question of time. The paper drop tanks that fell across Germany in 1944 and 1945 captured this industrial reality in a form that even a farmer in a distant field could understand. Here was a fuel container, made not of carefully machined metal, but of kraft paper and glue, used once and discarded without concern. It symbolized a war effort that could afford to waste what the other side could barely supply. For historians studying the air war over Europe, many strands contributed to Allied air superiority. Numerical advantages in aircraft and crews, technology in radar and communications, strategic bombing of German infrastructure, intelligence work, tactical innovation, and the cumulative grind of attrition. The P-51 Mustang and its drop tanks, including the paper tanks, were important components of this larger system, but not the sole determining factor. They are remembered because they so clearly represent the industrial principles underlying Allied success. The technical files preserved from RCIN and other facilities show how carefully German engineers documented these capabilities. Specifications, performance data, construction methods, and production estimates were all recorded with characteristic thoroughness. Modern historians, comparing those evaluations with Allied records, see that German technical analysis was largely accurate. Where German planning faltered was not in understanding individual weapons, but in grasping the strategic implications of the industrial scale behind them. A single P-51 was a formidable fighter. 10,000 P-51's, supported by an industrial base that could replace them as quickly as they were lost, amounted to uncontestable air superiority. The events set in motion in March 1944, when P-51's first escorted bombers all the way to Berlin, mark a turning point in that story. From then on, no target in Germany lay beyond the reach of American bombers protected by fighters. Strategic bombing could proceed with losses that, while serious, remained sustainable for the Allies. Synthetic fuel plants, ball-bearing factories, aircraft production facilities, and transportation networks came under repeated attack. Combined with Soviet advances from the east and Allied offensives from the west and south, this pressure helped bring about Germany's defeat within 14 months. Throughout that final phase, paper drop tanks continued to serve. Production ran through 1945, with thousands made each month. They were used not only by P-51's, but also by P-47's and P-38's, extending the range of all American fighter types. British fighters employed them as well. RAF Mustang squadrons flew long-range missions over occupied Europe and Germany, with paper tanks slung beneath their wings. By freeing aluminum and steel for other purposes while still providing needed range, the paper tanks exemplified the Allied habit of matching production methods to operational requirements and choosing efficiency over tradition. 80 years after those first Mustangs appeared over Berlin, the scene at Rechlin in March 1944 remains instructive. German engineers, standing in a hangar beside a captured fighter and later around paper cylinders laid out on workbenches, were not just learning about fuel capacities. They were confronting a deeper truth about the kind of war they were fighting. The paper drop tanks showed that the United States possessed industrial capacity beyond Germany's ability to match, that American engineering emphasized practical solutions over technical perfectionism, and that the Allies had enough resources to optimize for efficiency rather than improvise out of necessity. The engineers' understanding could not alter the outcome. By the time their final reports were filed, the war's end was already visible. Yet their work, preserved in documents and later studied by historians, illuminates a core lesson of industrial conflict. Success belongs to those who can sustain production, maintain supply, train replacements faster than they are lost, and apply resources with strategic purpose. The paper tanks themselves are now mostly gone, reduced to museum pieces and photographs. Their significance, however, lies not in the surviving objects, but in what they stood for. Each one, falling from a P-51 high above the Reich, marked the intersection of engineering, industry, and strategy. A disposable reminder that in modern war, the capacity to build enough in vast numbers can outweigh even the most refined technical masterpiece.